We've had voltage control on the network ever since we've had a network. And we've had automatic voltage control since we got rid of the substation attendants. You know, a couple of generations ago, we used to have guys in substations who were manually driving transformers up and down to keep the voltages at the right level. We then replaced that with a relay, a little box of tricks that did that for us. So we've had automatic voltage control for so long that guys like me just grew up with it. Now we're trying to take that on a stage.
Voltage control is a very important aspect of the control of the distribution network, and the onset of distributed generation has created a number of problems for networks in respect of voltage.
The current challenges for distribution network is to connect as much distributed generation to the network as possible without compromising the quality of supply to all the customers.
The impact of distributed generation on the network can be negative for voltage control. And traditionally, for voltage control, you're only measuring the transformer load current, for example.
Most voltage control, most conventional voltage control, you're essentially looking at your feet. So we have big transformers at big sites that are maybe feeding 10,000 customers. And the voltage it's managing, the voltage it's looking at, is the voltage at that major site. Now, to be brutal, nobody cares what that voltage is. That voltage doesn't matter. The voltage that matters is the voltage we deliver to our customers. They're the people that matter in this game. And so when you look at it, you think, well, maybe we're actually managing the voltage in the wrong place. So what we're looking to do is manage the voltage closer to the point at which it matters, closer to the customers.
It's actually quite a big step, because I think the way the network is changing, voltage regulation has to move down a level.
There are different solutions required in terms of voltage control, and we've designed and manufactured the relays and the equipment which can cope with the new requirements and challenges for the distribution networks.
Traditionally, the tens of thousands of distribution transformers which the DNOs own have offload tap changers, so they have 5 or 6 switching positions in order to modify output voltages of transformers. Now, if you need to change a tap position on a traditional distribution transformer, it requires an outage. Not great for consumers. So the on-load tap changer allows voltage regulation without those interruptions.
So we're pushing voltage control devices further down the network. So for example, the on-load tap changers at the secondary substations, instead of a group of 10,000 customers, we're talking about a group of a few hundred customers. So you've moved the physical control closer. But the really big step, and again, this is where wide area controllers like Gus come into their own, is saying, and we're going to raise our gaze. We're going to lift our eyes from staring at our feet to look out to where the customers are.
With our new technology, we choose to also measure outgoing feeder current measurements and incorporate that into the decision making for when to operate the tap changer and therefore influence network voltages. So that was used mainly as a monitoring tool to enable Gus to make its decisions.
What Gus gives us is a visibility right across the network. We've deliberately built the thing to take a view right down to where customers are, right across the low voltage network to where the customers are, to see what the voltages are on that part of the network, and use that to control the tap changes, whether at the secondary or even at the primary. So again, we have this combination that where what we have is a primary transformer that we can control, we can get more out of that with a better controller that raises its gaze from its own feet to look right out across 10,000 customers and say, well, okay, what's the right voltage to have here to give the guys who pay the bills the right voltage? And then as we extend the network by changing the transformers at a secondary substation to have an on-load tap changer as well, the control system will let us get the best out of those.
Smart grids heavily relies on telecommunications and all that good stuff, more digital SCADA.
Smart networks is all about communication between different parts of the solutions, different equipment, different devices, talking to each other, communicating with each other.
One of the main lessons is that we have to embrace all of those good things. The implementation of digital technology in order to make smart grid a reality. The main assets on the ground, like the transformers, yeah, we should be using them for as long as we possibly can, but the communications on top of that should take us a long way.
Conventional assets, novel hard assets, or novel control, a holistic solution, a unified solution, is going to deliver the most efficient and economical network that will give customers the best service for the lowest price.
I think the project was big success. There was challenges, but the project was definitely successful because this equipment is working at the substation. And now it's time to evaluate the performance of it. And now it's time to look how beneficial the solutions are to the business. The initial results are very promising.
I think this is a fascinating time to be involved in the power industry because you have these new challenges coming, customers wanting more, but also new solutions coming along as well. And marrying those two together is absolutely fascinating. We're all having to learn a whole bunch of new skills.
I spent a lot of time with Northern Power Grid commissioning engineer, on-site operations staff, and also with Siemens engineers trying to coordinate everything. And the level of skills I've gained, learning from other people, working with them quite closely, and managing the whole project, it was from time to time very challenging, but as well very rewarding.